All right, if you're a dev working in AI audio, you know the dream, right? To create a voice that's not just fast, but, well, human. For so long, though, it felt like you had to pick one, speed or quality. It was a huge pain. So in this explainer, we're going to dig into the technical story of GAN-based vocoders. These are the models that finally broke that trade-off, and we're going to focus on the specific architectural jumps that made all the difference. Okay, so let's get right into it. To really get what's going on under the hood, you have to realize that an AI doesn't hear sound like we do. Nope, what it sees is this, a MEL spectrogram. Think of it like a visual fingerprint for audio. It maps out all the different frequencies over time. This isn't sound yet, it's the blueprint for the sound. And this is the final, absolutely critical piece of the puzzle. This is what a vocoder spits out. Its whole job is to take that visual blueprint we just saw, that MEL spectrogram, and turn it back into an actual raw audio waveform. You know, the stuff our ears can actually process. And the quality of that translation, well, that's the whole game.
All right, so here's how we're going to break this down. First, we'll talk about why this whole vocoder thing is so tricky. Then we'll meet the OG GAN, the one that brought the speed. After that, we'll get into Hi-Fi GAN, which was the huge breakthrough for quality. We're even going to uncover its secret weapon. And finally, we'll take a quick peek at what's happening now on the new frontier.
So, at the heart of all this is one fundamental problem, a real tug of war between speed and quality. For the longest time, the models were either super slow but sounded pretty good, or they were fast but, yeah, they sounded like a robot from a 90s movie. The dream was to get both, and that's exactly where generative adversarial networks, or GANs, stepped onto the scene. So what the heck is a GAN anyway? Honestly, the best way to think about it is like a high-stakes game of cat and mouse. You've got two neural networks. One is the generator. Think of it like an art forger, trying its best to create a perfect, realistic piece of audio. The other is the discriminator. That's your detective, the expert critic whose only job is to spot the fake. They go back and forth, and this constant competition forces the forger to get ridiculously good. And that brings us to our first major player, GAN. You really can't overstate how important this model was. It was one of the first GAN vocoders to just shatter the speed barriers. We're talking way, way faster than anything that came before it. For developers, this was a landmark moment. It proved that real-time synthesis, maybe even on a phone, was actually within reach. So let's pop the hood on GAN's architecture. For a developer, this was pretty slick. The generator was a fully convolutional network using transposed convolutions to upsample the spectrogram. What that really means is that it was designed from the ground up to be parallelized, which makes it screamingly fast on a GPU. But the really clever part, the big innovation, was on the critic's side of things, something called the multi-scale discriminator. So what is this multi-scale discriminator, or MSD? Well, instead of having just one critic trying to spot the fake, GAN basically hired a team of them. You had one discriminator looking at the audio at its original quality, another looking at a slightly blurrier, downsampled version, and a third looking at an even blurrier one. It's like having critics listening for different things, one for the tiny details, another for the overall flow. This let the model catch imperfections at all kinds of different timescales. So here's the bottom line on GAN. The promise was absolutely delivered. It was wicked fast, over 2,500 kilohertz on a single GPU, and had a tiny footprint of just over 4 million parameters. Awesome for deployment. But there's always a but, right? The problem was quality. It just wasn't as good as the slower, older models. You could still hear those little digital artifacts that screamed, "I'm an AI." This was the problem that needed solving. And that brings us to Hi-Fi GAN. This was the real game changer. The team behind it looked at GAN's speed and efficiency and essentially said, okay, we can keep that, but what if we could also get state-of-the-art high-fidelity audio? It wasn't about compromise anymore. Hi-Fi GAN was about proving you could have it all. And you can see the evolution really clearly when you put them side by side. Hi-Fi GAN didn't just throw everything out, it was a smart upgrade. For the generator, they brought in a new idea called multi-receptive field fusion, or MRF. And for the discriminator, they kept GAN's multi-scale discriminator, but they added an absolute powerhouse next to it, the multi-period discriminator, or MPD. And that combo was the key. Okay, let's talk about that generator upgrade, the MRF. It's a really clever idea. Instead of just looking at the audio signal through one lens, it uses a whole bunch of them at the same time. Each one has a different receptive field, some looking at tiny fine-grained details and others looking at broader, long-term patterns. By fusing all those views together, the generator got way, way better at understanding and recreating the complex textures of human speech. That new generator was a big step up, for sure. But believe it or not, that wasn't the secret to Hi-Fi GAN's incredible quality. The real magic bullet wasn't a better artist. It was a much, much smarter critic. The breakthrough came from a really fundamental insight into the physics of sound itself.
The authors of the paper said it best. Modeling periodic patterns of an audio is crucial for enhancing sample quality. So, what does that actually mean? Well, at its core, sound, especially a voice, is made up of repeating periodic waves. It's got a rhythm, a pulse. And capturing that natural repeating structure is the absolute key. If you miss that, the audio just sounds synthetic and dead.
And right there, that was the big problem with older models. Even GAN's fancy multi-scale discriminator was basically tone-deaf to these periodic artifacts. It might catch a big, obvious glitch, but it was totally missing the subtle, unnatural repetitions that our ears can pick up in a heartbeat. It's those tiny imperfections that make us instantly recognize something as AI-generated. And this is where the multi-period discriminator, the MPD, comes in. It is such a clever piece of engineering. Instead of downsampling, it has a bunch of sub-discriminators that look at the audio in a different way. Each one skips samples to focus on a specific periodic interval. So one looks at every second sample, another at every third, another at every fifth, and so on. And here's the really brilliant trick. It reshaped that one-dimensional audio into a two-dimensional grid. By doing that, it can suddenly use all the super powerful 2D convolutional tools from computer vision to explicitly hunt for those periodic patterns that a 1D convolution would just miss. And the results of that clever architecture? Well, it speaks for itself. We're talking about incredibly high-fidelity audio running at a wild 93.75 times faster than real-time on a single GPU. This was it. This was the moment the trade-off was finally broken, and Hi-Fi GAN basically became the foundation for almost every high-performance text-to-speech system out there. So, once Hi-Fi GAN basically solved that core problem of speed versus quality, it laid the groundwork for the next big challenge. The new frontier wasn't just about fidelity anymore. It was about building on that foundation to create models that were even more robust and universal. A perfect example of this is a model called Big Vegan. It took the Hi-Fi GAN architecture as its starting point and made some key upgrades. For instance, it replaced the standard leaky ReLU activation with something called Snake, which is this cool function that naturally has a periodic wave to it, helping the model learn those patterns even better. It also swapped one of the old discriminators for a multi-resolution discriminator, which focuses on spectral sharpness. But the biggest thing, it was trained on a massive scale to be super robust to new speakers, new languages, even background noise. And this evolution is still happening today. We're seeing models like SpecDiff-GAN pop up. They take that solid Hi-Fi GAN foundation and mix in techniques from diffusion models. You know, the same kind of tech behind those incredible AI image generators. They basically teach the model to denoise a signal, which has a really cool side effect. It makes the whole GAN training process much more stable. For any developer who's struggled with training GANs, that is a huge deal. So what's the big takeaway for a developer here? It's this. The giant leap from robotic, clunky audio to voices that are genuinely realistic didn't come from just making models bigger or feeding them more data. It came from a core architectural insight. It came from designing a discriminator that could perceive sound more like a human ear does, by focusing intently on that inherent, all-important periodicity. So we've basically arrived at a point that was pure science fiction not that long ago. We now have AI voice that's fast, incredibly efficient, and getting scary close to a real person. The major technical challenges have been solved. So the question that's left for us, for developers, for everyone, it's no longer, can we do this? The question now is, what are we going to do with it?